Welcome to the AWS Certified Cloud Practitioner Prepcast, where we guide you through everything you need to know for your certification exam. Whether you're just starting or looking to refine your knowledge, this course will set you up for success. Brought to you by baremetalcyber.com. Let's get started. When approaching databases on AWS, it's helpful to first step back and consider the landscape as a whole. A database is simply a structured way of storing and retrieving data. But the variety of engines available on AWS reflects the diversity of workloads modern organizations face. Choosing the right engine isn't about picking the most advanced or popular technology. It's about aligning the characteristics of your data and queries with the tool designed to serve them best. Some workloads thrive on rigid structure, others require flexibility, while still others demand extreme speed or special handling of relationships. Understanding this landscape is the first step in making informed architectural decisions. By the end of this section, you'll begin to see AWS databases not as competing products, but as complementary options, each with its own sweet spot. Relational databases represent the most familiar type of engine for many practitioners, as they organize data into tables with rows and columns, using a predefined schema to enforce structure. Queries are performed with structured query language, or SQL, which provides powerful tools for filtering, joining, and aggregating data. AWS offers relational engines through Amazon RDS and Amazon Aurora, giving you the choice between open-source systems like Postgres and MySQL or enterprise engines like Oracle and SQL Server. These services take away much of the operational burden by automating backups, patching, and scaling. The relational model excels when data has predictable relationships, such as customers and orders or students and classes. Its strict schema helps ensure consistency, but it can sometimes be less flexible when your data changes rapidly or requires highly variable fields. Not all data fits neatly into the rows and columns of a relational system. This is where key-value NoSQL databases like Amazon DynamoDB shine. Instead of rigid tables, DynamoDB stores items that can vary in structure, each identified by a primary key for fast access. This makes it ideal for workloads demanding single-digit millisecond response times at virtually any scale. Think of a shopping cart, a user profile, or session data in a web application cases where quick lookups and predictable performance matter more than complex joins. Because DynamoDB is fully managed and serverless, you don't need to think about provisioning or scaling infrastructure. It expands seamlessly as demand grows. Of course, you trade off some of the advanced querying abilities of relational systems, but in return you gain unmatched speed and elasticity. Document stores extend the NoSQL concept by focusing on semi-structured data, often stored in JSON format. In AWS, this role can be played by DynamoDB as well, but more commonly, developers look at managed MongoDB offerings through AWS Marketplace or third-party services. The appeal of a document model is flexibility. You can add fields to some records without restructuring the entire database. This is especially powerful when working with evolving datasets, such as user-generated content, logs, or catalog entries with variable attributes. Developers appreciate being able to query documents with rich filters and nested fields, while operations teams benefit from AWS's managed approach to scalability and replication. It's worth noting that while document stores lack the strict schema enforcement of relational systems, this flexibility comes with responsibility. Without thoughtful design, collections can become messy and hard to manage over time. Another important category is in-memory caching, where speed is paramount. AWS ElastiCache supports Redis and Memcached, both of which keep frequently accessed data in memory rather than on disk. This reduces the need to repeatedly query slower databases for the same information. For example, a retail site might cache product details or pricing that doesn't change frequently, ensuring users get lightning-fast responses. Redis offers advanced features like pub/sub messaging and sorted sets, while Memcached provides a simpler, highly efficient caching layer. ElastiCache integrates with other AWS services and scales to handle large volumes of requests, making it a common ingredient in high-performance architectures. However, because memory is volatile, caches are not substitutes for durable databases. They're accelerators designed to complement them. Understanding when to cache and when to query directly is part of good system design. Some data challenges aren't about speed or flexibility, but about relationships. Graph databases like Amazon Neptune specialize in modeling and querying connections between entities. Instead of thinking in terms of rows or documents, imagine a network of nodes and edges, friends connected on a social media platform, or products linked by shared purchase patterns. Neptune allows you to query these relationships efficiently using graph query languages like Gremlin or SPARQL. Traditional relational databases can represent relationships through joins, but performance degrades when the connections multiply. Graph engines are optimized for traversing millions of edges quickly, making them indispensable for recommendation engines, fraud detection, and knowledge graphs. AWS manages the scaling, replication, and durability behind the scenes, allowing developers to focus on modeling relationships rather than building complex SQL queries that struggle under relational constraints. Time series databases represent another specialized category, designed for handling data points collected sequentially over time. Amazon TimeStream is AWS's managed service for this workload, offering optimized storage and queries for metrics like IoT sensor readings, application logs, or system performance monitoring. The benefit of a time series database lies in its ability to handle enormous volumes of timestamped data efficiently, while still allowing queries that slice and analyze patterns across days, weeks, or years. For example, a smart building might generate temperature and humidity readings every few seconds from hundreds of sensors. TimeStream automatically manages data lifecycle, moving older data into cheaper storage tiers while keeping recent data in memory for rapid analysis. This balance of speed and cost efficiency makes it an attractive option when your data's primary axis is time itself. Some workloads demand not just performance but also immutability, a guarantee that data cannot be altered once written. Amazon Quantum Ledger Database, or QLDB, is built for this scenario, providing a cryptographically verifiable transaction log. Unlike traditional relational or NoSQL systems, QLDB maintains a complete, append-only history of changes, allowing you to trace every modification without gaps or tampering. This is especially important in contexts like financial systems, supply chain tracking, or regulatory compliance, where proving the integrity of records is essential. You can think of QLDB as a ledger similar to a blockchain, but fully managed by AWS without the complexity of managing decentralized consensus. While it's not a general-purpose database, QLDB fills an important niche when trust and verification are central requirements. For large-scale analytics, Amazon Redshift provides a managed data warehouse that aggregates and processes structured data from multiple sources. Unlike transactional databases that handle real-time operations, data warehouses are optimized for heavy queries across massive datasets. Redshift allows organizations to load data from logs, sales transactions, or clickstreams, and run complex reports to identify business trends. A marketing team might use Redshift to analyze campaign performance across years of historical data, something ill-suited for a transactional database. Because Redshift integrates with the broader AWS ecosystem, such as S3 for storage and QuickSight for visualization, it supports end-to-end analytics pipelines. Scaling can be achieved with both cluster resizing and concurrency scaling, ensuring queries remain performant even as data volumes grow into the petabytes. This makes Redshift a central tool for data-driven decision-making in many enterprises. Alongside warehouses, AWS offers OpenSearch, a managed service for search and analytics on unstructured and semi-structured data. Originally based on the Elasticsearch project, OpenSearch enables you to index logs, documents, or event data, and then query it using powerful search syntax. This makes it a popular choice for building centralized log analytics systems, where developers and operators need to search across millions of records quickly. For example, a security team might ingest firewall logs into OpenSearch and then run queries to detect anomalies or intrusions. While it is not a general-purpose database, its ability to handle free text search and near real-time analytics gives it a unique role in the AWS database ecosystem. By positioning OpenSearch alongside Redshift, AWS covers both structured data analytics and the more fluid, exploratory analysis of logs and text. An interesting development in recent years has been serverless databases, and AWS Aurora Serverless stands out as a key option in this category. Traditional database instances require you to provision and manage capacity, even during idle periods. Aurora Serverless removes this burden by automatically adjusting capacity in response to demand, scaling up during traffic spikes and scaling down to near zero when idle. This makes it especially appealing for unpredictable workloads or development environments, where paying for idle capacity would be wasteful. Aurora maintains compatibility with MySQL and Postgres, allowing developers to use familiar tools while benefiting from serverless scaling. The trade-off is that fine-grained performance tuning may be more limited than with manually managed clusters, but for many organizations, the simplicity and cost efficiency outweigh this limitation. Serverless databases are part of a broader trend toward abstracting infrastructure management entirely. The choice between managed and self-managed databases is another important consideration. AWS managed services like RDS, DynamoDB, or Neptune remove much of the operational overhead by handling backups, patching, scaling, and high availability automatically. Self-managed options, where you run a database on EC2 instances, give you more flexibility and control, but require significant expertise and effort to operate securely and efficiently. The decision often comes down to organizational priorities. Is tight customization more important than offloading operational burden? For most, the advantages of managed services, especially in terms of security and resilience, are compelling. However, some legacy applications or specialized workloads may still require self-managed deployments. Understanding this trade-off allows architects to align database strategy with team skills and business needs rather than defaulting to one approach. When comparing databases, it's helpful to revisit the classic trade-offs of consistency, availability, and partition tolerance concepts captured in the CAP theorem. In essence, a distributed system cannot fully optimize all three. It must favor certain properties based on workload needs. Relational databases often emphasize strong consistency, ensuring every user sees the same result at the cost of potential availability during failures. No-scale systems like DynamoDB, however, might prioritize availability and partition tolerance, allowing eventual consistency where data synchronizes over time. These choices aren't about right or wrong. They're about aligning guarantees with user expectations. For example, a banking application must never show inconsistent balances, while a social media feed can tolerate slight delays in propagating likes or comments. Recognizing these differences helps you choose the engine that matches both technical and business priorities. Finally, selecting the right database on AWS requires a holistic view of workload, scale, latency, and cost. A small startup with unpredictable traffic may find Aurora Serverless ideal, while an enterprise with stable, high-throughput workloads might prefer provisioned RDS clusters for fine-grained tuning. DynamoDB offers near-infinite scale for predictable access patterns, while Neptune solves unique relationship-heavy queries. Cost considerations go beyond instance size. They involve licensing, storage classes, and operational overhead. Latency requirements may push you toward in-memory caches or edge-accelerated services. By mapping each requirement against the strengths of the available engines, you arrive at a selection that feels less like a gamble and more like a reasoned, evidence-based choice. In this way, AWS's broad portfolio becomes a toolkit rather than a puzzle, enabling solutions tailored to your unique needs. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Security is always the first pillar when working with databases, and AWS gives you a range of tools to strengthen protections. Every managed database supports encryption, both at rest and in transit, ensuring data is unreadable without the correct keys. At rest, Services like Amazon RDS, DynamoDB, and Neptune rely on AWS Key Management Service, KMS, for key handling. In transit, Transport Layer Security, TLS, ensures that data moving between clients and databases cannot be intercepted in plain text. Authentication and authorization are equally important. AWS Identity and Access Management, IAM, allows fine-grained control, mapping permissions down to actions like who can read, write, or administer databases. Network isolation adds another layer, where virtual private cloud (VPC) settings define what traffic can reach your databases. Together, these measures create a layered defense, much like securing a building with locks, guards, and surveillance. Durability and availability are the next concerns for critical workloads. AWS provides multi-AZ deployments for relational engines like RDS and Aurora, automatically replicating data to a standby instance in another availability zone. This ensures that even if one data center fails, your application can continue without disruption. Backups are automated and configurable, giving you point-in-time recovery for scenarios where data corruption or human error strikes. Replication goes beyond resilience, as read replicas can be placed in different regions for both disaster recovery and reduced latency for global users. For example, a financial application might keep its primary database in one region but maintain a replica in another to ensure continuity during outages. The combination of redundancy and automated recovery minimizes downtime, aligning database availability with the stringent expectations of modern businesses. Scaling read operations is a common challenge as applications grow. Instead of overburdening a single primary instance, AWS allows the use of read replicas and caching layers. A read replica is essentially a synchronized copy of your database that can handle queries, reducing the load on the primary. Applications can distribute requests intelligently, ensuring faster response times. Caching adds another dimension, using services like Elasticache to store frequently requested results in memory for near-instant retrieval. For example, a social media feed might cache user timelines, so queries don't hit the database repeatedly. The key is striking a balance. Replicas work well for heavy analytical queries, while caches excel for repeated, predictable lookups. Together, these strategies provide elasticity, ensuring the system can grow without compromising user experience. Disaster recovery patterns build on these foundations. AWS snapshots capture complete backups of your databases at specific points in time, allowing you to roll back or restore in the event of catastrophic failure. These snapshots can be copied across regions, enabling a global recovery strategy. For instance, if a natural disaster or major outage affects one region, a copy in another region ensures business continuity. Cross-region replicas serve the same purpose with lower recovery time objectives, RTO, as they are already kept in sync. Designing with disaster recovery in mind requires weighing cost against risk. Global organizations often invest in active setups, while smaller companies may find periodic snapshots sufficient. The central lesson is that planning for failure is not pessimism, it is prudent engineering. Performance tuning is another critical design element. Indexes, for example, act like the index in a book, enabling the database to find records without scanning every page. Without them, queries slow dramatically as data grows. But too many indexes can degrade performance during writes, much like adding too many bookmarks that constantly need adjusting. Partitioning spreads data across multiple nodes, reducing bottlenecks, but requires thoughtful key selection to avoid hotspots, where one partition gets all the traffic. DynamoDB highlights this challenge with its partition key design, where poorly chosen keys can overload a single node. Avoiding hotkeys requires anticipating access patterns and distributing load evenly. These optimizations might seem subtle, but they make the difference between a responsive system and one that crumbles under real-world traffic. Observability ensures you can detect and resolve issues before they affect users. AWS databases integrate with Amazon CloudWatch, offering metrics on CPU utilization, memory, latency, and throughput. Slow query logs provide deeper insights, highlighting inefficient operations that consume excessive resources. Query plans go further, showing how the database intends to execute a statement, often revealing opportunities for index creation or schema adjustments. For example, seeing a full table scan in a query plan signals inefficiency that could be resolved by a targeted index. Observability isn't just reactive, it's proactive, enabling teams to tune performance continuously and spot anomalies early. Without it, databases become black boxes, leaving engineers blind to the causes of slowness or instability. Cost optimization is an ever-present theme, as database expenses can escalate quickly. Instance class selection influences both performance and price, with larger instances offering more power at a higher cost. Storage types, whether general-purpose SSD, provisioned IOPS, or magnetic, also affect cost-performance trade-offs. AWS offers pricing flexibility through on-demand, reserved instances, and savings plans, allowing you to balance agility with predictable expenses. For example, a steady production workload might benefit from a reserved instance discount, while development environments remain on demand. Data transfer and backup storage also contribute to costs, reminding us that efficiency is not only technical but financial. The art lies in tailoring choices to workload characteristics, ensuring dollars spent directly translate to business value. Migrating to AWS databases requires careful planning, and the Database Migration Service, DMS, helps streamline the process. DMS can replicate your data from on-premises or other cloud databases with minimal downtime, supporting both homogeneous migrations, e.g., Oracle to RDS Oracle, and heterogeneous ones, e.g., SQL Server to Aurora, Postgres. The service continuously replicates changes until cutover, reducing disruption to operations. At a high level, the process involves assessing source and target compatibility, creating replication tasks, and validating results. For organizations hesitant about moving mission-critical databases, DMS provides a safer path, allowing incremental transitions rather than risky big bang cutovers. Migration is not just technical, it's cultural and operational, requiring teams to adapt monitoring, access control, and maintenance practices to new environments. The data lifecycle extends beyond active use. AWS offers tiering and archival strategies to manage storage efficiently over time. Lifecycle policies in S3, for instance, can move old backups into cheaper classes like Glacier, while databases like TimeStream automatically tier historical records. Retention policies enforce compliance requirements by ensuring data is kept for regulatory periods before deletion. For example, a healthcare system may need to retain patient records for 7 years, while analytics logs might only need 3 months. Managing this lifecycle is as much about governance as it is about cost balancing the need to retain important information against the risk and expense of storing everything indefinitely. Clear lifecycle management ensures databases remain lean, compliant, and cost-effective. Hybrid access to databases is often necessary when organizations maintain both on-premises and cloud environments. AWS provides connectivity through VPN tunnels or direct connect links, enabling secure and predictable communication between legacy systems and cloud databases. Security groups and network ACLs then define what traffic is permitted, enforcing least privilege access even at the network layer. This hybrid approach allows gradual migration or ongoing coexistence, such as when a company keeps certain sensitive workloads on-premises but leverages cloud databases for scalability. The challenge lies in managing latency and ensuring consistent security policies across environments. Done well, hybrid architectures can provide the best of both worlds, leveraging cloud agility while maintaining existing investments. Compliance is another dimension where AWS databases provide built-in support. Audit trails, whether through CloudTrail logs or QLDB's immutable ledger, allow organizations to demonstrate accountability and trace every change. Encryption features satisfy regulatory requirements like HIPAA or GDPR, while access reports show who has interacted with sensitive resources. For industries like finance or healthcare, compliance isn't optional, it is existential. AWS aligns its database services with certifications such as SOC, ISO, and PCI DSS, providing assurance to customers and auditors alike. Leveraging these capabilities not only keeps you compliant, but also simplifies audits, reducing the burden on security and compliance teams. In practice, compliance features become part of daily operations rather than last-minute hurdles during audits. Common pitfalls often undermine otherwise sound architectures. One recurring mistake is over-indexing, where too many indexes slow down write performance and add unnecessary complexity. Another is neglecting backups, leaving organizations vulnerable to catastrophic data loss from corruption or accidents. Perhaps the most serious error is leaving databases open to the public internet without adequate protection, a misstep that has led to countless breaches. These pitfalls usually stem from haste or misunderstanding, not malice, which is why awareness is so important. By learning from these mistakes, engineers can avoid repeating them. In AWS, services like Trusted Advisor can even alert you to misconfigurations, making it easier to catch issues before they become crises. From an exam perspective, one of the most valuable skills is mapping workloads to the appropriate AWS database family. A transactional system with strict consistency calls for RDS or Aurora. A high-speed gaming backend may lean toward DynamoDB. Analytics over historical data fits Redshift, while searching logs aligns with OpenSearch. Graph relationships belong in Neptune, while immutable audit trails find a home in QLDB. This isn't about memorization, but about recognizing the patterns each engine serves best. By practicing this mapping, you not only prepare for exam scenarios, but also build intuition for real-world architectural choices. AWS's broad database offerings become less overwhelming when seen through the lens of use case alignment. In summary, effective use of AWS databases starts with requirements. By identifying whether your workload demands structure, flexibility, relationships, or raw speed, you can narrow the options to the right engines. From there, layering in considerations of security, durability, scalability, and cost allows you to refine the choice further. The portfolio is broad for a reason. No single engine solves every problem well. Success lies in matching the shape of your data and the expectations of your users with the service designed for that niche. With practice, this process becomes second nature, turning database selection from an intimidating decision into a confident, evidence-based step in building resilient systems. That concludes today's episode of the AWS Certified Cloud Practitioner Prepcast. Be sure to tune in for the next episode and visit us online at baremetalcyber.com or cyberauthor.me for more resources, including news, mailing lists, YouTube videos, podcasts, and much more.